Graphs are ubiquitous data structures. They are often the preferred choice for representing various types of data, including social networks, citation networks, telecommunication networks, or some biological networks. Also, in natural language processing, we make use of graphs in a lot of different applications and in tasks. We have lexical resources often represented as graphs in which words are nodes, and the lexico-semantic relationships between different words are edges in those graphs. We also have a lot of knowledge bases in which entities and concepts are the nodes, and here the relationships between different concepts are often typed edges between those nodes in the graph. And we have a lot of other usages for that, like word co-occurrences or other semantic networks. So it's very crucial for us in natural language processing to be able to learn low-dimensional embeddings for both nodes and relationships in our graphs. Here is the outline of this part of the presentation on graph embeddings. Specifically, we are going to cover some of the techniques on node and relation embeddings. For node embeddings, we are going to learn what matrix factorization is, and we will see some of the random walk-based methods and some of the graph neural models for learning node embeddings. As for relation embeddings, we will have some of the unsupervised and knowledge-based techniques. And at the end, we are going to briefly some of the applications and evaluation techniques for graph embeddings. So here is a toy example illustrating why graph embeddings are useful and why do we need them. Here is a toy graph to show why graph embeddings are useful and why we require them. So we have a set of nodes and edges on this graph. Some of the groups or some of the clusters are shown by different colors. What we're expecting from a node embedding technique is to transfer this graphical structure into a vector space like this, a 2D vector space in which the structure of the graph or the structural properties of that graph is preserved. So if you look closer here, the red dots are close to each other in that graph. Similarly for the blue points, similarly for the purple and for the green. We are preserving the same relative positioning in the space. And apart from that, the relative positioning of different clusters is also preserved when we go from this graphical structure into this 2D semantic space of node embeddings. So one might ask, why are we doing this at all? So obviously this form of representation is much more algorithm friendly than the graphical structure. So here you can represent each node as two numbers in this 2D space or a vector of a sequence of numbers. Whereas here it is much more difficult to transform each node to a form that is machine interpretable or usable by different machine learning algorithms. Okay, let's start with matrix factorization techniques for embedding nodes. So let's see how this matrix factorization works using a very small graph. A toy example here, we have a graph with 6 nodes and a few edges in between them. So first of all, what we do is to construct something called an adjacency matrix for this graph. We have a matrix of size n by n, where n is the number of nodes you have in that graph. And the corresponding cell for each pair of nodes denotes if you have a relationship between those two, and otherwise you're going to have zeros. If there is an edge, you'll have 1, and otherwise you'll have zeros. So each of these rows, you can take them as a representation for the corresponding node or the embedding for that corresponding node, which is A here. But similarly to word embeddings, what we usually do here is to reduce the dimensionality here. Usually using some of these eigenvalue-based decomposition techniques like singular value decomposition. Because first of all, this vector is very large in size, and secondly, because it's very sparse. Usually different techniques in matrix factorization differ in their way of defining this notion of similarity. The example I provided here is one of the earlier models in which we consider only first order relationships between nodes using this adjacency matrix. But some of the more recent techniques take higher order relationships, like some power of this adjacency matrix, or some more sophisticated measures of similarity, like the Jacquard neighborhood overlap, or some other techniques for denoting this notion of similarity between these nodes in your graph. Techniques that are based on matrix factorization are usually not scalable to large graphs, which is the case for most of the real graphs we're working with. Because first of all, you have to construct a very large matrix, the adjacency matrix, and then you have to reduce the dimensionality of that giant matrix into a low dimensional space. And usually this dimensionality reduction step is very computationally expensive. A more recent model makes use of random walks on graphs in order to address this problem. So let's see how these methods work in practice. Using a toy graph here we have. Imagine we are looking to construct an embedding for this node here. Let's call it S10. First of all, what we do is to make a number of random walks on this graph. Maybe starting from here, which is maybe S5. We go to here, which is S6. Then maybe we go to S10. Then maybe we go to S12. Then we go here to S14. And maybe then S15, and we stop this walk. And we record this. We have S5, S6, S10, S12, S14, and then S15. We make another random walk here, maybe starting from here, which is probably something like maybe S8, then going to S10. This is another random walk that involves S10. We're looking to embed S10. Then maybe from there we go to S12 again, and from S12 we go here to S13, and from there we go here maybe to S17 and stop. So the second path is S8, S10, S12, S13, and then S17. And we make a number of other walks here involving, for example, S10. These walks are something like artificial sentences. These are like sentences in which instead of having words, you have nodes. So these are like artificial sentences in which you have a word or a node co-occurring with other nodes in its neighborhood. The rest of the processes is you use some algorithm like the word2vec or any other algorithm we have for learning word embeddings, and try to generate embeddings for the nodes we have here. The same way we're learning word embeddings for words in sentences, we learn node embeddings for nodes in their contexts. And contexts are nothing here but some random paths, including the target node we are trying to embed. So this is the idea behind DeepWalk, one of the prominent models in this category. Another prominent model is Node2vec, a more recent one, in which you have some parameters, specifically the bias parameter, which kind of controls the walk you have. It adjusts the tendency you have in your walk in order to stay in your neighborhood or to leave that neighborhood in order to explore other areas of your graph. Some of the more recent techniques also incorporate, if you have some extra knowledge, like if you have some labels for your edges or if you have some content in your nodes, they also incorporate this sort of knowledge in the process of learning embeddings for the different nodes in this graph. Random walk-based methods make use of neural networks in their training procedure. But they are not the only graph embedding techniques that are based on neural networks. And it's not surprising to expect other techniques that are based on neural networks for embedding graphs. One of the earlier type of graph neural networks is the autoencoder based model. And SDNE is one of the prominent models in that category. So here the idea is very similar to what we had in matrix factorization. But the way we compress or reduce the dimensionality of those vectors is different, and it is based on neural networks. Again, if you remember in matrix factorization, we construct an adjacency matrix in which each node is represented based on the connections it has to other nodes in that graph. So here, for example, node 3 is represented by these 4 ones and the other zeros. And the difference here is that instead of using some eigenvalue-based decomposition technique, we make use of neural networks in order to reduce the dimensionality of this representation into a compact representation. Similarly to matrix factorization techniques, here we have some limitations in scalability and in generalizability because the size of the input vector as well as the output vector is equal to the number of nodes in the graph, which can be very large depending on the application. And usually in real-world applications, we have very large graphs. Another category of graph neural networks is called graph convolutional networks, or GCNs in general. The name comes from computer vision and from convolutional networks. And these models have the ability to address the scalability and generalizability issue of autoencoder-based models. The basic idea here is very simple. You learn the embedding for a target node by combining the embeddings of the neighboring nodes. And for each of those neighboring nodes, you learn the embedding, the corresponding embedding, based on its own neighboring nodes. In an iterative manner, you learn the embeddings of all the nodes based on the neighborhoods. And the name convolution comes from CNN networks because the process of combining these neighboring nodes is similar to the convolution function or convolution procedure we have in CNNs. Specifically for a target node, we aggregate the embeddings of the neighboring nodes in order to learn an embedding for the target node. And usually different models differ in the way they do this aggregation. For example, in GCN, the aggregation is a simple element-wise mean between the neighboring nodes. Whereas we can have other types of aggregations. For example, in GraphSage, we have some concatenation between these neighboring nodes, in addition to some other improvements. But the main difference between different GCN models is the different aggregation strategies we have in combining the neighborhood. It is not only nodes in a graph that carry information and that we might be interested in embedding. We also have edges in a graph that might carry a lot of information, and we might be interested also in modeling relationships or edges in a graph. We use a lot of different knowledge bases in natural language processing. And usually in knowledge bases, you have labeled edges in your graph. So you have labeled relationships between different concepts or between different entities. For instance, in this toy example, we have born-in relationships between Noel and Granada, and also the child of relationship between Noel and Jose. In addition to preserving the information carried by nodes in this graph, we might be also interested in preserving relationships between different entities, like the born-in and child of. So we might be interested in having an embedding space like this that preserves both entities or nodes in that graph, as well as the relationships between different entities in that graph. This is a very rich literature. One of the pioneering works here is TransE, which tries to make an embedding space of both entities and relationships, and here relationships are taken as some sort of translation between entities in that space. There are so many variations like trans H, trans R, trans D, and so many other models here that we are not going into details of. But relation embeddings are not only limited to knowledge bases. We also have a lot of techniques that are unsupervised in nature and try to learn embeddings for relationships using text corpora and without resorting to any sort of structured resource or any other schema. And just to say very briefly here, we have different models. We have co-occurrence-based models, we have predictive models, and the main idea here is to learn relationships between pairs of embeddings. And the outcome of these models is something like this. So instead of having words or nodes represented in a space, you have relationships between pairs of words or pairs of nodes in your graph. So for example, here the red dots are hypernymy relationship, the blue triangles are the coordinate relationships, and the green dots are meronymy relationships. As you can see, similarly to what we had in word and node embeddings, the space is sort of clustered depending on the type of relationship we have between different entities. Let's also quickly discuss some of the applications and evaluations of node embeddings and relation embeddings. As for node embeddings, node classification is one of the oldest and one of the most popular applications and also evaluations of node embeddings. So the idea here is for you to assign labels to nodes based on some given rule learned from a label subset of the nodes you have. For instance, if you have a semantic network like WordNet, you'd like to assign labels like domain labels to different concepts in that graph. Or maybe in a social network, you'd like to assign some labels to different users. Similarly, we have clustering, in which the idea is similar, but you do not have any class labels. So clustering, you might assume some sort of community detection in a social network, or some sort of clustering different concepts in a semantic network in order to reduce the fine granularity of that semantic network. In node ranking, the problem is given a target node, you'd like to recommend the top k nodes according to some given criteria. For example, similarity between nodes. And this might have different applications like friend recommendation, like question answering, or some personalized advertisement. Graph visualization is another popular application for node embeddings. You'd like to have some low-dimensional visualization of a large graph, which might be useful in interpreting or in finding different patterns in that graph. So for example, the graph here we have is some visualization of the cosmic web. And usually graph visualization involves some sort of dimensionality reduction like PCA or TSNE. We might also have network compression as a way of evaluating node embeddings. So reconstruction error is usually deemed as a good evaluation measure for node embeddings. So given a set of node embeddings, you try to reconstruct the structure of the original graph. And if the reconstructed graph is similar to what we had originally, then we say that the node embeddings have preserved the structural properties of the original graph in a good manner. As for relation embeddings, probably the most widely used application is link prediction. So the task here is to predict missing edges in a graph. Also, you can use link prediction for verifying existing edges, especially if you have some knowledge that some of the edges in your graph are spurious due to some construction procedure that have introduced some noise in your graph. And it can have a lot of applications like enriching different semantic networks or different knowledge bases in natural language processing. And in terms of social media, maybe it's friendship suggestion between different nodes in your graph. Also, it's been shown that unsupervised relation embeddings can be beneficial to many language understanding tasks, including reading comprehension, relation extraction, and common sense reasoning.